All right, these notes are covering section 4.3 in our notes in our textbook. We break this section 4.3 into two parts. So the homework, the first homework listed at the bottom will be 4.3.1, and then the second part will be 4.3.2. Okay, so in this section we're talking about logarithmic functions or logarithms. And so for most of you, logarithms are something that's totally new to you, something you've never seen before. And so logarithms were useful back before we had calculators, handheld calculators. They were useful in something called the slide rule. Now, I don't have a slide rule with me here at home when I'm making this video, but it's the kind of the precursor to the calculator, and it used logarithms to do calculations rather quickly. Okay, for us, logarithms are going to be sort of another way of rewriting an exponential function. All right, so let's just, when you first start talking about these, it's going to seem really strange. You're going to feel a little fuzzy-headed when you're like, what's this? Why are we doing this? How does this work? But with enough practice, it'll kind of become more clear. Okay, so just accept the fact that at first it's going to seem very strange, but eventually it'll be sort of second nature. Using these logarithms will come second nature to you. Okay. So to start with, we'll be able to convert them from logarithms to exponents. We'll be able to convert back and forth, but eventually you'll get to a point where you feel comfortable just using them with logarithms. Okay, so let's say for all real numbers y and any positive numbers b and x, also the one more restriction on b, it can't equal 1, cannot equal 1. So and they can't be negative. They can't be 0, they can't be negative, b cannot be 1, then y equals, so again, we're doing a function here, so y equals log, and then this b is smaller, it's like, almost like a subscript. It's smaller and lower than the rest of the letters, so it's log base b, so the number that's down here, it's usually going to be a number, is what the base of the log is. And again, none of this is going to make sense until we play around with it a lot, and then you'll feel more comfortable with it. So log base b of x. So x is the argument of the logarithm. Okay, so y equals log base b of x, and that's equivalent to an exponential function, or equation, I guess would maybe be a better way of looking at it right now. So x equals b to the raised to the y power. So if we look at these two things, converting between them, the base of the logarithm is the base of the exponent. So that's the first place I think of when I'm converting. The base of the logarithm is equal to the base of the exponent. All right, so b raised to the y power equals x. That is equivalent to saying y, the y is by itself, so the exponent on the exponent on the exponential equation is the value that's over by itself, and so is equal to log base b, so the bases are the same. Log base b of x equals y is equivalent to x equals b to the y. Okay, and again, that's going to be like, what? But once you play around with it enough, it'll become second nature too. So the expression log base b of x represents an exponent in which b must be raised so that it will equal x. So b raised to some value equals x. So the logarithm says this whole logarithm is equal to y. This whole logarithm, the base raised to some power, the base, right? Logarithm of the base. So log base b of x is equal to the value you have to raise the base to make it equal to the argument. So what would I have to raise b to make it equal to x? Well, you can see y is what I would have to raise b to make it equal to x. And so that's what this is. Again, first couple times it's going to be really confusing, but as we play around with it, it'll make more sense. So try converting. Pause this video and convert this exponential equation into a logarithm using sort of these rules up here. All right, so I always start with the base is the base. Log base b, because that's the base of the exponent, it's the base of the log, make it smaller and lower. Log base b of n equals p. So this whole logarithm is equal to the value, p, that you'd have to raise the base to make it equal to the argument n. All right. So when you read this out, it's log base b of n. That's how we read the left-hand side of that. Don't say log of b of n. Don't use the extra of in there. So it's log base b of n. Of n, that is the argument of the log of base b. Okay, so try the same thing then for this equation. Again, I'm going to use the base as the base, log base 2 of y equals x. Okay, so let's play around with this whole idea of exponential equation and its inverse. We talked about inverses. Remember, inverses are reflected about the identity line. So here is a function, y equals 2 to the x, and that's this here, y equals 2 raised to the x power. That's this function here. We graphed exponential equations in the last section or so, and you can see this one. I tried to over highlight it in green ink to kind of emphasize it, different from the other thing. It's kind of dark, you can't really tell it's green, but so I drew this one in. You have it, I think, on your paper. Okay, and then I dashed this identity line. All right, so let's find the inverse. We talked about how to find inverses. Remember, the first thing we do is we flip the x with the y with the x. So x is equal to 2 to the y. Now we want to solve this for y. Now the problem is that y is up in the exponent. We can't get that y out of the exponent. We don't have any way of doing that, except we might be able to convert this thing to a logarithm. So convert this thing to a logarithm. Remember, the base is the base, so log base 2 of x equals y. So I've gotten the y by itself. And you might write the y over on the left because that's kind of what we're used to. So that is the inverse of that function. And you can see that's what we've got here. This is y is equal to log base 2 of x. All right, so these are inverse functions of each other. All right, so a logarithmic function is we can convert it. Here, we didn't just convert it. We flipped the x and the y with the x. So, these aren't inverses of each other here, but these are inverses of each other here because we flipped the x with the y and then solve for y. So the whole point of one of the reasons we do logarithms is it's a way of getting a variable out of the exponent. Okay. So notice these two functions are inverses of each other. Y equals 2 to the x, y equals log base 2 of x. Those are exponentials. Let's look at the domains. So this one, the domain is all real numbers. All right, what's the range? This one has a limitation on the range, right? This is asymptotic. Remember when we graphed exponential functions? It's asymptotic at the lower end. So the range can't be 0, but the asymptote is at 0. So we start above 0 up to infinity. Now this is the inverse, so I don't really even have to look at my graph. I can just look at these things. I know my domain should be 0 to infinity because the range becomes the domain becomes the range, and the range is negative infinity, all real numbers, negative infinity to infinity. So this helps us with, if you look at this, we have restrictions on the domain. Notice x has got to be positive. And that's what we were talking about up here. Positive numbers b and x. That x has got to be positive. So does the b. I mean, here we have a 2. We don't have the general b. We have number 2 as our base. But x, again, we had to be positive, and we see that here. It's got to be positive. Can't be 0, can't be negative. And we see that because we have a vertical asymptote here. This graph will get closer and closer to the y-axis, but never touch it. So that's why it kind of agrees with what we're talking about here. It kind of agrees with the restrictions that we had up there. Okay, let's play around with some logarithms then. Okay, so first rewrite each of these exponential, write each as an exponential equation. Well, I guess this one is exponential, so let's convert this first one to a logarithmic equation. All right, so again, the base is the base, so the base of this exponent is 10. So we have log base 10 of 1,000 equals 3. Remember, this logarithm, this whole logarithm on the left side here, this has got to equal the value that the base gets raised to make it equal to the argument. So log base 10 of 1,000 has got to be equal to 3 because the 10, the base, raised to the third power is the argument, and that's what a log does. Okay? All right, convert these then to an exponential. So the base 5 raised to the x equals 25. Okay, and so often what we'll do, to at least to start with, we can convert this to an exponential. Now we can probably, if we were going to solve this, we weren't asked to solve this, but if we wanted to solve this, then we just make the basis the same, right? So 5 to the x equals 5 squared, so clearly x equals 2. But also I know it's 2 over here because remember, this whole thing, this whole left side, is equal to the value you got to raise the base to make it equal to the argument. So 5 raised to what power is 25? So that whole thing is equal to 2, which is what x is, and we can see that here, x equals 2. Okay, next one, convert that one. So think about what solving it as well. We'll eventually get to solving, but we can think of that. What would I have to raise 8 to? What value would I have to raise 8 to make it equal to 1? Or we can convert this. So we can say 8, the base, raised to the x power equals 1. Well, 8 raised to what power is 1? I think you would say, well, that's really what they're asking us to do, is convert it to an exponential equation. But we can see here x would be equal to 0. Just like here we saw x was equal to 2. Not really what they're asking us to do. They were really just asking us to convert it, but we can think about solving some of those as well. All right, solve each equation. So this is log base x of 1/64 is equal to -3. So if at this point we're not really great with solving these things yet. But what we can do is convert it. So the base is the base. So x raised to the -3 power equals 1/64. Now 1/64 can be written as what? It can be written as 4 to the -3. So you can see x is equal to 4 here. Okay? X is equal to 4. All right, going across to number 6. 25 raised to the 1/2 power should equal x. All right, so if we convert that, 25 to the 1/2 power equals x. Well, I think we all can see that x equals 5. All right, 27 raised to the x power equals 81. 27 raised to the x equals 81. Now, I can't really figure out what x is, but if we could make these bases the same, I think we could say this is 3 cubed is 27. So 3 raised to the 3x equals 3 to the 4th. The bases are the same, so we can make the exponents equal. 3x equals 4. And so x equals 4/3. So what power would I have to raise 27 to make it equal to 81? Well, I would want to take the cube root of it, that would be 3, and then raise 3 to the 4th power. So taking 27 raised to the 4/3 power equals 81. But that one's hard to do just as a logarithm. Eventually, maybe you'll get comfortable enough to jump to this answer. But when in doubt, convert it to an exponential equation and solve it. All right, let's look at number 8. So this is saying what? Convert that. So 9 raised to the 3/2 power equals x. So x is equal to 27. Right? The square root of 9 is 3. 3 cubed, 27. All right, next one. This whole thing is equal to the value you'd have to raise 16 to. So 16 raised to what power is equal to 2? So you might be able to do that in your head already, but if not, convert it. 16 to the x equals 2, and now make these bases the same. That's 2 to the 4th is 16, so 2 to the 4x equals 2. 2 to the 1, if you will. And so that means 4x equals 1, or x equals 1/4. So 16 raised to the 1/4 power equals 2. So this whole logarithm, right? This whole logarithm is equal to the value you have to raise the base to make it equal to the argument. So 1/4. All right, so let's use the next couple of examples to develop some rules. Log base 7 of 7 to the 4th. Remember, this whole thing is equal to what you'd have to raise the base to make it equal to the argument. So 4 raised to what power? 7 raised to what power is 7 to the 4th? So I think you'd all see that that is 4. So this whole thing is equal, or could be simplified to 4. Because it's the power that you would raise 7 to. So 7 to the 4th equals 7 to the 4th. Okay. All right, log 5 raised to the log base 5 of 25. So we could evaluate what log base 5 of 25 is. The base 5 raised to the 2nd power equals 25. So we could convert that whole exponent, which is a log base 5 of 25, to a 2. So 5 to the 2, that's equal to 25. So notice, it's not a coincidence that 5 and that, the base of this exponent and the base of the log are the same number, and the answer is just 25. So using that same kind of pattern here, I don't know what log base 3 of 10 is. 3 raised to not any normal nice number is 10. Now we know 3 squared is 9, so this answer's got to be a little bit more than 2 for sure. But then we take 3 and raise it to that power. Does that make sense? So using that same pattern, I think you might see that this is equal just to 10. So when this 3 and that 3 are the same, it's just equal to 10. So we've looked at we've been able to develop a couple of rules from here. So the first one is when we have log base b of the argument b raised to the x. That's just equal. So what value do you have to raise the base to make it equal to the argument? In that case, that's just equal to x. And then a different problem, if I have b base raised to the log of the same base of some value x that's equal to x as well. Okay, so those are two rules that we sort of will use from time to time. Okay, some other things that we can talk about. We've seen this in previous section. When the bases are the same, we can simply set the exponents equal to each other. So we can say that x plus 2 is equal to 2x minus 4. And now we can just solve this, bring the x over, so that's going to be x, add 4 to both sides, so 6. So x equals 6. All right, the next one. So if you're not sure what to do, convert it to an exponent, or an exponential equation, I guess. All right, so the base 2 raised to this power, 4, equals the argument, which is x plus 2. So 2 to the 4th, that's 16. So we have 16, and we subtract 2, so x is going to equal to 14 here. All right, log base x of 25 equals 2. We want to find x here. So I can convert it. X to the 2 equals 25. Now we would take the square root of both sides. Now normally we would take the square root of both sides and we would say plus or minus 5. But x in this case is the base of a logarithm. And you remember our rule up here. The base has got to be a positive number. Can't be 0, can't be negative, can't be 1. All right, so when we take the square root of both sides here, we know x is going to be equal to 5 only. Yes, plus or minus 5, but if I was just solving this by itself, yes, I would want to say plus or minus 5, but that x, the thing we're looking for, is the base of a logarithm, so the base cannot be negative. Okay. This one here. So with this, the variable's over by this side. So what I would say is work the inside out. So log base 4 of 2. So hopefully you've gotten enough work with your logarithm. You can tell me what log base 4 of 16 is. So log base 4 of 16. So remember that whole thing, that whole logarithm is equal to the value you have to raise the base to make it equal to 16. So 4 raised to what power is 16? So that whole thing can be replaced with just a 2. So we have now log base 2 of 2 equals x. And so what is this logarithm equal to? Again, what do I have to raise this to have it equal to the argument? So x is just equal to 1 there. All right, now this one's a little bit trickier. I can't work from the inside out because I don't know what log base 2 of x is. X is unknown. So what we really want to do is sort of work from the outside in. So convert that to an exponential. So log base 3 of some argument, like I'm keeping my finger over it because I just want to think of it as like a variable, my finger. So log base 3 of my finger equals 0. So convert that. So that means 3, the base, raised to that power, 0, equals my finger. So that means 3 to the 0 equals what was my finger? Log base 2 of x. All right, so this is an exponential. 3 to the 0, that's easy. That's just 1. So I can erase that and put a 1 in. All right, log base 2 of x equals 1. Convert that. 2 to the 1 equals x. 2 to the 1 equals x. So x clearly equals 2. All right, let's go on to 18. That looks familiar, right? It looks like one of our rules. So we can say log base 5 of 5 cubed, that's just 3. If you have to, worst case, set it equal to x, convert it, right? 5 to the x equals 5 cubed. The bases are the same, x equals 3. But, you really should look at this and be able to identify it as one of our rules. All right, what's this one? Log 8 raised to the log base 8 of 2x. Again, that's this rule. So this is just equal to 2x. All right, and the last one. Log base 27 of 3 equals what? So that means 27 raised to what power equals 3? And hopefully you see that that's 1/3, right? So that's the cube root of 27. 27 raised to the 1/3 is the cube root of 27. That's equal to 3. Okay. Number 21. So we can figure out what log base 4 of 16 is, and I think we can figure out what log base 8 of 2 is, and then that's just a multiplication dot. So we multiply them together. So log base 4 of 16, what does that equal to? I think that you can see that that's 2 times what's log base 8 of 2? So 8 raised to the what power is 2? I think you can see that's 1/3, right? The cube root of 8 is 2, so that's 1/3. So this is 2/3 equals x. All right. It says solve, and that's kind of what we're doing, but really we're just evaluating this side, really. And, of course, that's equal to x. So we just have to evaluate these, really. Even though they're saying solve, it's just find what x is. All right, log base 3 of 1 over 27. Think about what that is. 3 raised to what power is 1 over 27? Well, if it was 27, it would be 3 cubed, but it's 1 over. So I think you'll see that it's -3, right? The negative exponent makes it 1 over it. So that whole thing, that whole logarithm is equal to -3, because 3 raised to the -3 power is 1 over 27. All right, plus, so 64 raised to what power is 4? And I think if you think about that, so 64 raised to what power? Not a negative this time, but a fraction, right? 1/3. The cube root of 64 is 4. All right, and so if we combine, that would be -9 thirds plus 1, that's -8 thirds is what x is equal to. Okay? All right, so this is the homework for tonight. It's just having you practice some of what we've been doing on this page. But then also for homework tonight, look ahead at the next page and try to see some patterns. I made some specific problems that will help you try to develop a rule. If I have log base b of n plus log base b of m, what shortcut could I do? What could I do with that? And these examples are kind of geared to help you sort of visualize that. So work through page 2 of these notes. I'll do them on the next video, but before that video, go ahead and do this homework, but then also work at filling out this page 2 of the next page of notes.